Good evening, everybody. This is Kim Malville. I'm a retired professor in astrophysical and planetary sciences, and Bob Grossman from ATOC and I have been organizing this series of distinguished professor seminars for the past year. This is the 15th that we put together every month, and we have indeed been very pleased and proud to present talks by our very finest professors on the campus. Before we start, I'd like to tell you that this program is being recorded, and if you have any questions, please put them in the chat box at the bottom. Tonight, our speaker is going to be introduced by Bob Anderson, who is the chair of Geological Sciences and a distinguished professor in his own right, from whom you will hear something in the future. So Bob, I turn the program over to you.
Okay, thank you very much, and good evening to all. As Kim says, I am Bob Anderson, the present chair of the Department of Geological Sciences and a fellow of the Institute for Arctic and Alpine Research, or INSTAR. It's my great pleasure to introduce Gifford Miller to you all, as he is a colleague at both of these units. Giff has been here at CU since his PhD several years ago, several decades ago, in fact. He's led each of these units, both the Geological Sciences as chair and INSTAR as its director, and has been instrumental in the construction of both the geology building and the SEEK complex in which INSTAR is presently housed. But I want to focus on his science. Bottom line is that you're in for a treat. Giff has spent his entire career studying the history of climate and how that history has manifested itself in the environment. He ably followed his mentor, John Andrews, in studying Baffin Island, that huge landmass to the left of Greenland, and has spent countless summers tromping that island, extracting tale after tale from its fjords, from its moraines, from its lakes, and from the little shards of dead vegetation that encircle the now dwindling ice caps that dot its summits and that he is pointing to in this picture. But what is remarkable about Giff, at least to me, is that he has as well a big intellectual footprint in the Southern Hemisphere, something he won't tell us much about today, I think, in particular in the red center of Australia. There, he and a team of biologists and geologists have proposed a remarkable storyline that connects the demise of giant birds with the arrival of humans on the continent 50,000 years ago. And they take that inquiry a step further to surmise just what about the arrival of humans led to this extinction. So in Giff, you have someone who has studied climate for decades, has extracted the coolest of stories from both hemispheres. He has something of Midas touch in that regard, and is a gifted teller of those tales. He's also trained a strong and widespread set of graduate students who are and will further his work. Giff, congratulations again in your selection as a distinguished professor here at CU. It's well deserved. The floor is yours, and we all look forward to your talk.
If I can't share my screen until that's gone. There we go. Okay, does that look all right?
Wonderful.
Beautiful.
All right. Thanks, Bob, for that slightly exaggerated introduction. It's really a pleasure to be here and to share with you some of the interesting results that have come out of our work in the Canadian Arctic, and provides an Arctic perspective on contemporary warming. And as Bob said, I both hold a professorial position in the Department of Geological Sciences. I'm a member of INSTAR, and I acknowledge here on the right the support I've received over many years from the National Science Foundation, which has been critical to being able to do most of this work. So talking about global warming, is global warming a theory? Because that appears on the covers of a lot of magazines out there. And no, really global warming is simply a fact. And so this is the record of planetary temperature, global temperature on an average. This happens to be the one NASA puts together. Several others have done it. And that's, all of them look about the same. But just because we know it's warming says nothing about why it's warming. There's no attribution in this. This is simply the fact that the planetary temperature over the last century and a bit has on average been increasing, and it's increased, a little over a degree C from the turn of the last century. And there's also nothing in there that tells us whether this warming is particularly unusual. And in order to start to address some of those questions, we need to look back in the past to provide a perspective. And so that's what I'm going to try to do today, is to put the contemporary warming in a longer perspective and see if we can answer some of these questions. So here's a view probably many of you have seen. This is the average of the last 5 years of the second decade of the current century of the temperature anomaly. And so several patterns come out of this. This is a NASA reconstruction. They all look about the same. But obviously the Arctic is warming the most, and the scale is a little hard to read there, but we're looking at something like 2 to 3 times faster than the planetary average. Northern hemisphere is warming more than the southern hemisphere, mostly because there's a lot more land in the northern hemisphere, and the land is warming faster than the sea. There's a little bit of misattribution there because the ocean is actually absorbing much more of the actual energy that the planet's gaining. And it's just that it's being stored in the surface waters, which are about 100 meters thick. So there's more energy being stored in the ocean, but the magnitude in terms of temperature change isn't as large. And then there's this little weird blue hole up here that, if there's time at the end, I want to say a little bit about that. That's just started to appear and has attracted a fair bit of attention. So because the Arctic is warming as fast as it is, ice is melting, probably nowhere better than Greenland. Can we see that? And so how do we know? Well, you can go there. This isn't my picture, but you can see it's melting, but it's very hard to get a spatial pattern of melting because it's a really big ice sheet. And the satellites are really good at seeing these kinds of changes. And probably the best is this set of 2 satellites, the GRACE satellites. So we put 2 satellites up there fairly close together in the exact same orbit, a specific distance apart, and measuring the distance between the 2 satellites with great precision. And so as the leading satellite approaches Greenland, and it's set up in an orbit that takes it over Greenland, the mass of the Greenland ice sheet, the gravity of that, attracts this leading satellite, and the distance then stretches between the 2. And when they pass over the ice sheet and it's leaving, the leading one then gets pulled back by that gravitational attraction. And the precise measurement of the changes in the distance allows us to reconstruct changes in mass of the Greenland ice sheet. And so here's about a 15-year record. And you can see that every year in the winter, it gains mass from snowfall, but in the following summer, it loses more mass than it gained in the winter. And so this gives us a quantitative metric of both the magnitude of mass loss, and this pattern that's emerging on the ice sheet itself shows you both the pattern and magnitude of the warming, which just over this 15-year window of time has been increasing tremendously. And so we now have Greenland melting virtually over all but the very highest portions of the ice sheet itself. So that's a consequence of the Arctic warming. And the other really big part of the cryosphere in the Arctic is Arctic Ocean sea ice. And again, it's very hard to observe that from the ground because nobody lives up there. So our record is really limited to the satellite record starting in 1979. A lot of interannual variability in Arctic Ocean sea ice, but there's undoubtedly this negative trend in loss of the area covered by Arctic Ocean sea ice throughout the year. You can do this on any season, and in all seasons that coverage is changing, and as that highly reflective ice is replaced by open ocean where most of the solar energy comes in, this intensifies the warming there. So we really want to know when the Arctic Ocean sea ice is going to disappear because it's such a strong positive feedback on the warming. And I'll give you a quick video of why it's so hard. So this is a radar view, which allows you to see through clouds. And the Arctic Ocean is typically pretty cloudy, but it illustrates these major features where you have a very large Beaufort gyre over in the Canadian basin over here. It's always in motion. Ice is being exported down the east coast of Greenland and through these inter-island channels in the Canadian archipelago up there. But because of this dynamic term, it's extremely difficult to precisely model how quickly that ice is going to disappear. You have to let that play out. Besides the area that's decreasing for sea ice coverage, and probably more importantly, the thickness of the sea ice is also changing. And satellites are very good at telling the difference between heights. And thick ice is buoyant. So the thicker it is, the higher the ice sits above the adjacent sea surface. So here's going to be about a 25-year animation from NASA of changing thickness of Arctic Ocean sea ice between about 1900 and I think 2016. And you can see this for decades, there's been very, very thick, stable sea ice across northern Greenland and across the Canadian archipelago. And that ice is now being entrained in this gyre and exported down the coast of Greenland and melting out in the North Atlantic Ocean itself. And here in just a second, you'll see that the difference in ice thickness between, say, 2016 and 1900 over that little time period is really tremendous. And what's important with that is that this very thick ice here is robust. It resists wind churning, the wind crashing together, so it stabilizes sea ice. Now that we've got mostly just first and second year sea ice, if a big storm works up in the Arctic Ocean, this thin ice starts breaking apart, and as it breaks up, the much more surface area of the ice exposed, and it can melt much faster. So most people think that the timing of the disappearance of sea ice may well be related to major storms that make it break up even faster. And so both of those terms are leading to us to have an Arctic Ocean that's ice-free, at least in the summers, in the not too distant future. So I have a little anecdote to share here, and anecdotes aren't really science, but it's a little bit about sea ice. So a long time ago, I was working up in the Canadian Arctic, and we travel around in these little freighter canoes, and there's a bit of a tide. So this is sea ice that's been exported from the Arctic Ocean and on the coast. We see it all the time. And the only reason I have these pictures is because there happened to be this one kind of pretty chunk of sea ice. So if we look at it there, it's sort of nice. And I actually had my field assistant standing next to it for scale, and we photoshopped him out of there. But one of the peculiarities of the Arctic is capturing scale is difficult because there's nothing up there that's of a predicted scale. There's rocks and ice, but none of it is fixed. So imagine a person standing next to this ice, and how big might they be? And I'll bring Harvey back here. And so there he's about a 6-foot guy there. So, and this was what we saw all the time. Nothing unusual about it, except this was unusually attractive. And I've been back almost every year since then. And in the last decade and a half, we don't see this anymore. It's simply gone. So that's not really science. It's an anecdote, but it's consistent with the science that you've seen from the satellites, that this robust, really thick sea ice is simply gone now. So, so what? It's fair to ask. So what? Climate's always changing, and you'll hear this pretty frequently. There have been ice ages and warm times throughout Earth history without any assistance from humans. So why should the current warming be any different? And if we can't answer that, we can't convince anybody that there's anything to be done about it. So we really have to think, how can we really evaluate this kind of question to decide whether the climate change that we can observe is something that we really should be alert about. And one of the problems that is the shortness of our record. And so here's again the temperature record. And if you sort of twist your head sideways and squint a little bit, you could imagine that there's some sort of multi-decadal beat behind the changes in the temperature. And so are there any things in the climate system that beat on multi-decadal timescales that we might think are causing this? And it turns out that there is. There's the Atlantic multi-decadal oscillation. So this is basically the average surface water temperatures of the North Atlantic Ocean. And this has been monitored for a long time because it's used in hurricane predictions. When the North Atlantic is really warm, the fuel for hurricanes, water vapor comes out and you expect more. And it's beating in these same time periods of multi-decadal. And so this is unforced natural variability. There's no human role in this beat that's coming out of the North Atlantic. So it leads to this question then, do some of these unforced multi-decadal cycles explain some or even all of the observed warming? What's their role in that? Or conversely, are we looking at forced variability? So is the Earth adjusting its temperature in response to specific changes in the variables that determine the planetary energy balance? And the problem for us with the instrumental records is they're simply too short to resolve that record. So we're going to have to look into historical data to try to address which of these two plausible mechanisms for explaining the contemporary warming. And so I want to just take a second to look at what sets the planetary temperature. So if we're looking at the planetary energy balance, there's not a whole lot of terms there. The energy, we have two sources of energy. One's the sun and the other one's radioactive decay from deep within the Earth's interior. And it's the sun's temperature that determines how much energy is coming to the Earth. And the heat sources from within the Earth, although they're measurable, they're so small that they're in several places out in the decimal places. So we're going to ignore that. So we know something about the sun's temperature. Ever since Earth was a baby, the sun has been getting a little bit hotter all the time due to some pretty simple physics out there. But on a 100-year time scale of the observed modern warming, there's no change. So we can ignore the sun. The other piece of the sun's temperature is the 11-year sunspot cycle. And for the last 20 years, the sun has actually been getting a little bit cooler. And so that's when most of some of the strongest warming. So there's no explanatory power in changes in the sun's temperature that's consistent with a warming planet. So we're going to dismiss that. The other term is, of course, how far the Earth is from the sun. And on 100-year timescales, there's no change there. And as we'll see, if we get onto longer timescales, there's some small variations in that we're going to have to look at. So we're really left with the planetary reflectivity and the greenhouse effect as the only variables we can think about. And the albedo or the reflectivity isn't a forcing. If sea ice goes away and shiny light that reflects the sun is replaced by an ocean that absorbs it, that makes it warmer, but something's got to make the ice disappear. So it's a very strong feedback, but it can't cause the changes. So it's not a forcing. So that leaves us really the only term that we can mess around with to try to explain changes is the Earth's greenhouse effect. And of course, most of you certainly have seen this picture. We've been measuring atmospheric CO2 concentration since 1957. And not only has it been increasing all the time, but the rate of increase has itself been increasing. So CO2 is a greenhouse gas. It's a plausible driver of the change. So that's consistent. And then this was a press release that just came out earlier this month from NOAA that the increase in atmospheric methane, which is the other strong greenhouse gas that's got an anthropogenic source from it, set a record increase just last year. So both of these changes are consistent with a warming world. And of course, the really major greenhouse gas is water vapor. And as the ocean's warming, the rate of evaporation is increasing. So water vapor is also increasing. So the three major greenhouse gases all are increasing. So those are plausible drivers. But these records don't tell us anything about how unusual is this. How do we know that CO2 didn't change by itself sometime in the past? And so really, how important is this? And to answer that, we're going to turn to paleoclimatology. And I'm going to start with CO2, and I'm happy to see that Jim White's in the crowd because I'm going to use some of the data that he's been involved with. And so we use ice cores through the big ice sheets, through Greenland. This is the summit of Greenland in Antarctica. And one of the things that these ice cores give us is this special character of trapped atmospheric gases. So as the snow that falls on the ice slowly converts to ice, and the air slowly diffuses from it, some of that air is captured in these little tiny bubbles. And we can melt that ice, extract the bubbles, and measure the concentration of greenhouse gases at the time the snow was deposited. We do that mostly in Antarctica, and I'll show you the Antarctic record here next. So this is 800,000 years of record through the Antarctic ice sheet. They're trying to push it back to about 1 million. They think they can get it that far back. And we're plotting the CO2 concentration on the y-axis here. And so what you're looking at in these ups and downs is the coming and goings of the ice age cycles of the last 1 million years. When CO2 is high, those are warm times when all the big northern hemisphere ice sheets are gone. And when CO2 is low, that's when much of northern North America was under a giant ice sheet that was something like 3 miles thick. And that change is about 100 ppm in this scale over here. And then we come to the modern times. Here we come out of the last ice age. Here's all of human civilization as we know it. And here's the record of ice of CO2 now since 1957, going up to 420 ppm. So there's more change in the amount of CO2 in the atmosphere in the last 100 years than all of these ice age cycles. So that at least gives a perspective that this is a very unusual time in Earth history, way outside of the natural variability at least on 1 million year timescales. So knowing that CO2 is now higher than any time in 800,000 years, is there any evidence that we can find that this warming has raised the planetary temperature well above what we would consider normal variability? And so we're going to go to paleoclimatology to do that. And so I'll take you up to the Canadian Arctic, and the bottom left there is North America, and in the yellow box is Baffin Island, the largest of the islands in the Canadian Arctic archipelago, sort of right next to, adjacent to Greenland there, with a lot of high relief, but lots of ice that's over there. And all of that white that you see there are bits of ice. So summers are warming, glaciers are melting, so they are shrinking. So what controls glacier size? And there was a really nice study that Fritz Kerner, a Canadian glaciologist, he took all of the detailed studies that glaciologists do, where they go out and they measure in great detail the snowfall, the distribution of snow in the winter and how it melts in the summer, and then determine the relative importance of snowfall versus summer melt. And what they found is that well over 90% of the mass balance, so that's whether the mass increases in an annual cycle or decreases and is melting, more than 90% of that is explained by summer temperature. And so changes in glacier dimensions then become an ideal proxy for changes in summer temperature, because that's the dominant term, more than 90% on whether a glacier grows or shrinks. And I like this one. You know, we have lots of ways at looking at old temperatures. We use pollen and plants, but unlike biology that has spent the last 3 billion years developing strategies to avoid being impacted by climate change, glaciers have no brain. They have no strategy for survival. If it snows more than it melts, they grow. If it melts more than it snows, they shrink. So they're really an ideal proxy for changes in climate. The other thing that I only appreciated as I got into this study is this passive-aggressive nature of glaciers. And so here in the foreground, you see the classic glacier flowing rapidly, carving out a valley through this granitic terrain, bringing lots of debris that it's eroding from beneath and along the sides, plumes of meltwater with fine-grained sediment floating on denser seawater coming out here. That's the aggressive glacier. But if you look up in the highlands here, we have thin layers of ice sitting on relatively low relief landscapes. This is the passive portion of the ice, and better shown in a slide here. So now we're looking up high here. If you can see it, is the aggressive glacier now with lots of ice chunks flowing rapidly. One in the foreground here you can't quite see. And here's this flat land in thin ice, and this spectral character here, this marks where this ice was in about 1950. And it's been receding since then. There's about a half a kilometer of recession there. And I'm going to take you to that spot right there. And we're going to look at the edge of that ice. So here's the ice. And if you look in the foreground, you'll see a little red pocket knife and a triangular piece of rock. And there's the pocket knife and the rock. We're less than 1 meter from the ice edge. And I'm an Arctic guy. This is like looking at a giant forest. This is like everything's home there of these plants. all the lichens on the rocks. There's moss and liverworts in here. This is everything that ever grows, and it's just come out like 2 weeks before we got there because the ice is receding about 10 meters per year, and it's perfectly preserved. So what we do is we take a sample of that moss and we radiocarbon date it, and this particular one was 1,200 years. And so what these dates tell us, they tell us when the climate got cold, the snow lines, or the line where snow doesn't melt, dropped, the glacier advanced across this site. It didn't erode it, it didn't disturb it because it was frozen to its bed. And the site's been continuously ice covered until the summer that we were there and collected it. So that's given us some information. It also tells us the date. It dates the last time summers were as warm as the present. And we put this on a century time scale because glaciers have a response time. It gets warm and the glaciers melt slowly. So we think of it as a century time scale. So we could say that the summers of the past century are warmer than any century in 1,200 years, is our take home from that one. So this is now giving us a longer perspective of contemporary warming. So once we've found that this was a common phenomenon, we spent a lot of time over about a decade wandering around the edges of these thin little ice caps, looking for these preserved plants that had been entombed beneath the ice and tell us when temperatures were as warm as today. And here's another one here. You can see this nice, here's the very edge of the ice cap, and here's some of these plants. So we've done this now over pretty much all of Baffin Island. And there we go. So there's all the sites where we have data. And here's as a scale, this is something like 700 or 800 kilometer stretch over about 10 years. And we have, in this case, we have just over 300 different glaciers where we have a radiocarbon date on plants that are right next to the ice. It just had come out the year that we collected them. And we're going to look at what those dates then tell us. So here's an example of something that we would get right next. Here's the glacier right next to us. And when we get a radiocarbon date, we get the age, the best estimate of when it was last alive with a certain uncertainty that has some structure to it because the radiocarbon content of the atmospheric CO2 changes a little bit all the time, and we have calibrations for that. And we take all of those radiocarbon dates with their uncertainties, and we stack them together in a probability density plot, which is here. So this is probability of a date against time over the last 10,000 years. And so we don't have any dates back here, but we have a bunch of dates 4,000 years ago. There's over 60 dates in this clump here, and then a bunch of younger ones too. And those of you are familiar with the Little Ice Age, what you're looking at here is an abrupt beginning of the Little Ice Age, about 1250 in the Common Era, and an intensification as time goes on. So the take home from this that we can say then is that the current century, the warmth of the current century is unprecedented in more than 4,000 years. Because 4,000 years ago, it got cold, ice advanced across these sites, and it remained continuously over those sites until it's melted out today. So now we've got sort of a multi-millennial perspective on contemporary summer warming in this portion of the Arctic. So you might ask, okay, how come it was getting colder back here? How come the ice was growing and killing plants? And here it keeps growing and keeps growing and keeps growing. So what's driving the climate system? What is the change in the energy balance that allows the Arctic to get cold? Because that'll help us to answer how come it's getting warm. And so we have to look then at this peculiarity of Earth's orbit around the sun. So the orbit isn't circular, it's an ellipse here. And the sun isn't at the center of the ellipse. It's at one of the two foci. So sometimes we're close, and this is an exaggeration, but it makes the point. Sometimes we're closer to the sun and sometimes we're farther from the sun. And this is north up in both cases here. So our summer is when we're tilted towards the sun. So currently, the Earth is farthest from the sun in the northern hemisphere summer. So our summers are cold, relatively speaking. They're getting less energy than at other times. If we go back 11,000 years ago, the Earth was closest to the sun in northern hemisphere summer. And that change in energy is about 9% more solar energy in the northern hemisphere summer 11,000 years ago than there is now. And then for the last 11,000 years, we've been migrating across this pattern to where we are now at the farthest point you can get. So from first principles, we would expect northern hemisphere summers to be warmest 10,000 years ago, gradually cooling as the northern hemisphere moves farther from the sun during the summer. And the solar energy is still decreasing slightly due to these orbital terms, but the planet's warming. So you can't use the sun to explain any of the warming because we're still getting less of the sun. But you can use it to explain why this got colder, because it was warmer back here. There's no ice growing till about 4,000 years ago. But here's the oddity. We have 30 different ice caps where we've collected these little plants that you can't put on this plot. They don't match any of these dates. So let me show you two of them. And they all come from this setting, really high. This is a high summit, sort of hard to tell that from here, about 1,600 meters above sea level. And you can see the spectral character here, this change from light to dark. What's harder to see is there's a cliff here, and you're looking at a cliff in the front, which is hard to tell from this perspective. So as this ice cap grows, when it got colder, it grew to this edge, and then it falls off the cliff. So it can't grow very thick because it falls off when it gets much thicker than that. So this is its margin. So we went to this cluster of rocks right here in the center, and we found plants, and their radiocarbon age was 45,000 years. So we did not expect to find that. Here's another one. Again, you can see better this cliff here. So here's the residual ice that's all that's left of it. When we made the collection, it's probably a lot smaller now. And you can see how once it gets very big, it starts to just fall off the edge. So it can't ever get hugely thick, maybe 50 meters or so. And the radiocarbon date there is beyond the limit. It's more than 46,000 years. So there's 30 of these that we found where the dates are basically more than 40,000 years. And the most boring slide ever, there's all the dates. I won't spend any time on that. But we can now say with considerable confidence that the summers of the last century were warmer on average than any century in at least 40,000 years. So now we're really starting to get a much better perspective of how unusual the contemporary warming is, at least in the Arctic areas where it's warming so fast. But we can ask then, well, when do we really think? Because this is just the limit. The radiocarbon clock has run out on us. So it could be considerably older. And we can ask when in the recent past might Earth have been warmer than the recent centuries. And to do that, we go right next door. Here's Baffin Island. Here's all those dates. We go to Greenland, where the ice core through the center of Greenland goes back about 130,000 years. And it's going to provide a better context of what might be the true age of these samples. And so here's the plot of oxygen isotopes. And the main thing to think of is that up is warm, down is cold. Here's the last 10,000 years on the left here. This is when we were closest to the sun, so it was warmer, and then it's been getting steadily cooler, not hugely cooler, but as the Earth has moved farther from the sun in northern hemisphere summers. And as we go back in time, 40,000 years, this is really cold. We're in the middle of the last ice age. And so as we wander back, it's only when we get back to about 120,000 years that we see a time when Greenland tells us it was warm, maybe warmer than present. And the reason for that is due to these orbital terms. Not only was the Earth closest to the sun in this time in the northern hemisphere summer, but the Earth's tilt, which has a wobble to it. So sometimes we're more tilted, sometimes less. The more tilted we are, the more energy comes into the high latitudes, as you can imagine. And so this was a special time when those two terms coincided. So when the Earth was closest to the sun in the northern hemisphere summer, the tilt was at its maximum. So we got something like 12% more solar energy coming in at that time. And it led to nearly the complete disappearance of the Greenland ice cap. Not quite, but it melted a lot of it. So we think probably that, and hiding behind here as we speculate that the age of our old vegetation is probably 120,000 years at the end of this, as the ice advanced at the end of this last warm time. So we can say then something to the effect that Arctic summers currently are the warmest in 120,000 years. So that really starts to put this perspective that we can't gain in any other way on how unusual the contemporary warming actually is. So what? I don't live in the Arctic. Why should we care if the Arctic's getting so warm? Well, unlike Las Vegas, what happens in the Arctic doesn't stay in the Arctic, right? So as you know, when we start to make predictions for the future, and the IPCC report was just sort of officially released. This is the report that comes out every 4 or 5 years, taking stock of what the future is going to look like. What can we predict about 2050 or 2100? And most of those predictions have high uncertainties, but there's some predictions that have extremely accurate uncertainties. And for some reason, that's hiding back there. But this prediction has 100% confidence. There's zero uncertainty. Sea level is rising and sea level will continue to rise into the future. There is zero uncertainty on that. The uncertainty comes in the magnitude of the rise and the speed at which it rises, and whether it's regular and predictable or whether it may have some abrupt hiccups in it. So here's the satellites do a really good job of sea level as well. It's very difficult to measure sea level precisely because continents are moving, the ocean's wandering around, currents shift. But we're looking at something like 3 or 4 millimeters per year and increasing. So with you thinking that in the next century, there may be a half a meter or a couple of meters. And the consequences have been mapped out quite thoroughly, and I won't go through that here. But there are certain areas that are more vulnerable, and if you were looking for a place to put your retirement investments, I wouldn't choose Miami, but other areas might be safer. But this is a significant impact. Even small rate rises in sea level significantly impact the human enterprise. What matters then, as we look into the future, is like how much and how fast these large uncertainties are there. If sea level rise is predictable, if it's constant and predictable, we're incredible at adaptation. This is one of our greatest strengths. And we can move Miami, we can move New York City as long as we can predict reasonably how fast sea level will rise and it stays regular. And the only way it won't stay regular, if it's just the melting of the ice sheets and the thermal expansion of the ocean as the ocean warms, we can predict that pretty well. But if the ice starts to move really quickly, and in Antarctica, if the ice shelves, you hear a lot about ice shelves, as the ice shelves break up, it releases the ice shelves holding back the glaciers coming off the main ice sheet there. It's possible that you could get really rapid, abrupt rises in sea level, and that's extremely hard to adapt to. So those are the really big uncertainties. Abrupt rise gives you serious challenges. The other one is the dreaded polar vortex. And so there's a high speed jet at high elevation that for the most part contains the really cold air into the high Arctic regions. And that's set, the speed of that jet is set by the gradient between the equatorial regions and the polar regions. Because the polar regions are warming 3 times faster than the equator, the gradient is diminishing. And as that gradient diminishes, the speed of the polar vortex decreases, and then it starts to wander a little bit, like you see here on the right. And occasionally you get these outbursts of cold air that come all the way down to Texas and places like that don't expect that. And so one of the sort of ironic future predictions is that we're likely in a warming world to get outbursts of really cold air as the polar vortex weakens and you start to see these bulges of air extending well down into the mid-latitudes. So that's another Arctic consequence that affects impacts the low latitudes and why we should be paying attention to the Arctic regions. And then finally, here's that little hole in the warming up here. So many of you are familiar with the Gulf Stream, this flow of very warm, very salty water that comes off the coast of Florida and out into the North Atlantic current and brings really warm water that keeps the Brits and the Ouijays from freezing to death up in here. But as that warm, salty water gets to the high latitudes, it cools. Because it's very salty, it eventually gets dense enough that it sinks, and it sets up the large-scale, slow ocean overturning current. And one of the places that sinks here, and the other one is in this spot down here. And if the water can't sink, this current can't flow there, because it's able to flow here because it disappears into the deep ocean here. And so there's some concern whether this lack of warmth in the surface water here is related to melt from Greenland or something that might slow this down. It's still not doing that, but there's a lot of people paying attention to it, because if this current were to shut down, there's a whole movie about this that's not particularly accurate, but it gives the basic story that much of human activity in this northwest part of Europe is dependent on the warmth that's provided by the Gulf Stream and the North Atlantic current. So just a quick wrap up here. What should you do about this? We should do something. So we can, I think, have a very solid conclusion that the planet's warming due to increases in carbon dioxide and methane from fossil fuel burning. So we're in charge of what's going on. And there's some other greenhouse gases in the background there too. But these are results of anthropogenic activity, an indirect effect of industry across the planet. And so when we think of what you should be done, the first thing, this is from my perspective anyway, is acknowledgement. I mean, we have to, and this is slowly increasing, it's sort of encouraging that there's much more discussion about planetary climate warming now. And the thing is that this can't be the United States agrees to it or Europe agrees to it. It has to be global, because the only response that'll make a difference is if it's a global response. And one of the problems of acknowledgement is that to make any changes is expensive. It's going to cost dearly money. And so the part that's hardest to acknowledge, though, is that the cost of doing nothing is even worse. We can't afford to do nothing. It's too expensive, because to make any changes, if we wait, the longer we wait, the more expensive it gets. So that's a tough one that we haven't crossed that one yet. And then it's adaptation. You know, change is going to come no matter what we do. So there is no stopping those changes. We already have the terms in the atmosphere with the greenhouse gases that are going to continue to warm the planet, and the feedback mechanisms, the positive reinforcement of that, are strong, and they're not going to be stopped. So we're going to have to adapt. So that's important. And then we want to mitigate. And to mitigate just simply means to slow things down. And one of the important things that often gets misused, I think, when we look at what the future might be, is like, it's not the end of the world. If we take the equilibrium state of CO2 at 400 ppm that we've got right now, we have examples from the past. If you go back to the Pliocene, this is like maybe 5 million years ago, CO2 was about the same as it is today here. And if you could have landed on Earth in the Pliocene, you would have said, damn, this is a nice planet. There's no ice anywhere in the Northern Hemisphere. You could be growing crops in Northern Canada or in the Russian plains. So the equilibrium state isn't the problem. The transition from where we are now to a stable state is the dilemma, and the rate of change is the struggle that we've got to keep up with. Is the reason that we need to mitigate the change so that we can manage the rate of change and adapt to it. And I think I'll just wrap it up there. I have a couple more slides, but it looks to me like we've got covered pretty much everything, and I'm happy to answer any questions people might have.
Thank you very much, Giff, for a sobering and very precise presentation. of the situation with regard to climate change. We are asking Dean Miller, Jim Miller,
White.
Jim White, I'm sorry, Jim White, to join you in the question and answer period. Jim, yes, here you are. So we invite any questions or any comments that Jim might have or anyone else. Go ahead.
So GIF, one of the concerns we have is indeed the rate of change, as you pointed out in your last slide. What do we know about the rate of change of climate change in the past? Is that something that we can pull out of the paleo record as well?
If that's a question to me, I'd probably put it back in Jim's court, because it's his work that has actually told us some of these things. I mean, when they first started to get together to take a core through the Greenland ice cap, Greenland ice sheet, I was a little skeptical as to what they might learn, and because it was a really expensive operation. And the thing probably that was the most surprising that came out of the isotopic measurements, that many of which were made in Jim's lab, was that as we looked back into the past, it was clear that there were extremely abrupt changes where the climate system, at least in the North Atlantic, went from something like full glacial extreme cold to something getting close to modern. And I think that we used to say in the time it takes most people to graduate from university, it was something like less than a decade's worth of time. And so that really raised something that no models had ever predicted, is that some combination of ocean atmosphere shifts could result in, at least regional, across, say, the North Atlantic region, into these really abrupt shifts in the climate system that are beating on times that are measured in years to a few decades, not centuries and millennia.
One of the points you made was that we could move New York and Miami, which we can do. I agree, but to where? Are there? So it's rate of change is one thing, but are there stable points in the sea level rise history that you think might exist where you say, all right, this is a safe spot to rebuild Miami, at least for the next century or two?
Yeah, really good question. I think if I can spin it a little bit, in order to move Miami, there has to be a place to move it to. And in the US, we probably have some places, but if you were to go to Bangladesh, which is living on a giant delta not very far above sea level, we're going to have to move those folks. And the dilemma is that where they want to move to, somebody's already living there. And so that's conflict. And the military is actually ahead of the curve on this. They've been thinking about these sort of war games that if sea level rises and people have to move, and there's people already in the place you want to move to, then you get conflict, and conflict leads to wars. So I think that doesn't address your question of stable positions, and you might be able to respond to that yourself. But I think the greatest talent that humans have is the ability to adapt amazingly well and be very clever at doing these things. But there's a limit to our ability to make those changes that in some areas is likely to lead to conflict, and there's ocean, island nations that were simply going to disappear, and those people aren't going to start treading water. They want to go somewhere too. Now, I'd be interested to know whether you think, Jim, that there may be some stable points where sea level is, once you get rid of the ice shelves and West Antarctica goes, is East Antarctica going to be happy living where it is?
So, as you know, it's imprecise, but I think the best guess we have is that something on the order of 13, 14 meters of sea level rise is tied up in very, as you described it, the active ice, the aggressive ice. And once that is flushed into the ocean, then sea level rise slows down and your more passive ice becomes the driver. So if you look at the history of the planet, 13 meters is about what you would see. And interestingly, 400 ppm CO2, we are likely to eventually see 13 meters of sea level rise. So I guess the analogy is the thermostat's already turned up. The water of the ocean just hasn't warmed up yet because it takes a long time for the water to warm up. If you've got a question in the chat, and I'll read it to you. The rate of change of a mean value, especially if it is rapid, is dependent upon the intensity and the number of extreme occurrences. Is this observed in the record? I'll start there.
Yeah, and can I share my screen? Is that, I mean, because I'll show basically Jim's record, I think. Let me just bring that up because it's relevant to this topic. Does that show okay now?
Yeah.
Yeah, so here are the classic extreme events. Whoop, there it comes. And so here, you know, so this is a proxy for temperature that Jim's team has been measuring in the labs. Several other teams around the world have been doing this. And this is a time scale. So these lines are almost vertical. So they're saying that we're getting really abrupt changes. And then they're followed by much slower recoveries back to this cold state. But there's not really much of a trend in here. So this isn't a change, but these are perturbations in the system. And I think it's telling us that there's some threshold event that occurs that explains this really rapid rise in temperature, something about the ocean atmosphere circulation in the North Atlantic. And then there's a slow millennial scale recovery back to some mean state in the background. So I think there's information to be gained from this that might be useful in looking at future change. I don't know that really answers the question in the chat. But
I guess the question in the chat also gets at this issue of the number of changes as maybe not opposed to, but in combination with the intensity of the change driving the mean state up. And I would just point out that in this particular plot, finding a mean state is not an easy thing to do.
Right.
And is it terribly informative?
Yeah. Yeah, and I guess the other take home from it is that in the few warm states we've got, which is the last 10,000 years and this little window back here at 120,000 years or so, there are no extreme events that are appearing there. And so, you know, we are now in this unusual situation where we are in a warm interval of time, and we're having an extreme event in the energy balance of the planet anyway, and we're watching how that plays out. And you know, at least in the Arctic, it's an event of 1 in 100,000 years, and if we look on the CO2 time scale, it's a 1 in 5 million year event. You know, we do have, you know, the Earth record. The Earth has run these wonderful experiments for us in the past, and that people, you know, are trying to understand. And there's back in the Paleocene, Eocene, there's an event where there's an abrupt warming that's probably greater than the warming we're observing here, that we think is related to an abrupt release of a whole lot of greenhouse gases. So it gives us one sort of experiment in the past that we might be able to learn something from, but it certainly resulted in a dramatic change in the mean state of the system. But it doesn't look like it's a repeated event. It's one event that did a major perturbation in the energy balance of the planet that took a few million years to recover from.
If there's any other questions in the chat, just put them in. One of the things that I think you've had the privilege of doing over time is being in the Arctic, seeing, I mean, you showed us an example of, you don't see these big chunks of ice anymore. So tell us about your experience. You know, you've lived through, you know, probably one of the biggest climate, or the beginnings of one of the biggest climate changes in Earth's history for a long time. I mean, what has it been like to be in the Arctic over that time period?
Let me share a little story. Back in about the middle of the 1970s, we were working on Baffin Island, and we hired an Inuit two guides to come with us with a whale boat, which they were left over from the whaling days. And we did a really long travel. We were out for about a month. And on the way back from that trip, we had a huge rainstorm, one of the biggest rainstorms. You don't get a lot of energetic things up there, but it was, and we're all huddled under tarps and things. And you could hear this little bit of thunder in the background. And the two guys were Joeli and Lipa. And Lipa came back to us and he said, "We want to know about thunder. The Inuit think there's one thunder in the world. And every decade or so we hear it. It wanders around the planet, and every decade or so we hear thunder." And so I asked him about lightning. He didn't know the word. So I described lightning, flashes of light coming out of the sky and coming down or going between clouds. No, never heard of lightning. And then fast forward to 2015, we're working on central Baffin Island. We're up on these ice caps up 1,000 meters above sea level, and there's huge thunderheads and thunder and lightning striking all across the landscape. And our main concern was trying to decide whether glaciers are conductors or insulators, because we were the highest thing on the landscape. But it's an anecdote. Here we've got, and I've talked to people who worked up there in the 60s in these exact same places we were. They never saw thunder or lightning, but the atmosphere is just more energetic, and we're getting these big thunderheads with lightning striking around. And so that's just sort of an example of the kinds of changes that have taken place. And just before COVID, the last time I was able to get up there, two of the old men who were little kids when I first started going there, we sat down and actually recorded them and said, what do you see that's different? What's your experience? These are Inuit who are traditional hunters and trappers, and they would describe the birds that they see now. And the thing that made me most annoyed is that now we get black flies up there. There were never black flies up there when we first started working there. So they had a lot of these tangible examples of how the warmth was impacting. And interestingly, the sea ice, we think of sea ice as going away. Maybe that's a good thing. They can travel more. But what they're finding is the sea ice is less reliable. They used to be able to, in September, the place froze up. You got on your dog team or your skidoo, you went out trapping, and then you came home again. And now the ice just breaks up. There's sometimes when they can't travel the entire winter north of their little town because the ice is in constant motion. So sort of almost the opposite of what you might have predicted might have been beneficial to them has actually caused them a lot of problems because the ice is no longer dependable like it used to be. So those are just a couple of examples of the kinds of things that in one lifetime have changed, and all those local Inuit folks up there could talk for hours on how these things have impacted their way of life.
So if you don't mind, I'll just share a similar anecdote. I've been going up to the top of the Greenland ice sheet for many decades, too many. And I had never seen a rainbow on top of the Greenland ice sheet until about 4 or 5 years ago, because it doesn't rain, it snows. And so one day we actually had rain, and there was a big rainbow, and it was, people were like gawking at this. We'd never seen that before. So it's similar. You're seeing weather phenomenon, you're seeing animal changes that are just really outside the bounds of any norm that you might expect. But so you raise an interesting point with your Inuit colleagues up there. What do you think is their future? I mean, they're you know, for a long time they had the Arctic to themselves because it wasn't a very attractive place to go, except for you and a few intrepid souls. What's the future of the Inuit, in your opinion?
Yeah, I almost might say climate change is the least of their challenges. I mean, these are people, you know, when we first started going there, all the men that we traveled with were born on the land in little, you know, huts that were made out of whatever driftwood they might find, and so they were 100% traditional folks, and when, you know, after the Second World War, when we were worried about the Russians, we built the dew line. That completely changed the social structure of the Arctic, and all the local little tiny settlements were forced into these now Western-made communities with little tiny boxes and houses. And that really raised a challenge to that social structure of how they had lived their lives for thousands of years. Most of these people have traditions that go back several thousand years in this area. And I think that how you manage that challenge of sort of an imposed structure that fits with a mid-continent North American lifestyle, where you have oil heating and electricity and freezers, with that traditional way. And sort of the classic example to me is you go to somebody's house and they say, "Are you hungry?" And you go, "Yeah." And they go to the freezer and they bring out a chunk of frozen seal, and they take their axe out of their hatchet and they chop out some of the frozen seal. So here you go. Have a bite of seal. And that juxtaposition of a tradition of eating raw meat and living like that, inserted into sort of a 20th century heated house, was sort of illustrates that struggle between trying to maintain a traditional life that so many of them had been brought up in, and make that transition to a cash economy where you work 8 hours a day and go home to your family. So I think that challenge is even greater than the climate change challenge for them, myself.
That's a great insight. Kim, do you want us to wrap this up?
Yeah, I want to thank Jim White, our dean, and Giff for a very fascinating discussion between you two. And I especially want to thank Giff for a absolutely marvelous talk with great depth. And I want to remind everyone that this is recorded. So if you would like to hear him again, it's there for the asking. Our next talk is going to be by Tom Veblen, who almost by accident is going to discuss the same issue of climate warming, but in connection with wildfire and forest ecology. And I'm so pleased to have these two talks back to back. Tom has been studying the health and fire hazards, fire of other times using tree ring dating, and he is going to bring us another really fascinating discussion of one of the central issues of our lives, climate change, but also for us living in Colorado and the Front Range, the threat of wildfires. So that's going to be, as you can see, on May 18th. We look forward to seeing you all again at that time. Thank you, Giff, and thank you all for coming. Good night.
Good night, all.